here I'm just showing you a couple of slides that sometimes you want to examine your alignment, right? For example, here we have a sequence that has very many gaps. You might want to remove it, but you might also want to retain it. I say it depends, okay? Whether, you know, removing it is a good idea because maybe it's too short, or maybe if it's still useful to give you good phylogenetic signal, okay? So that decision should be made depending on the pathogen that you're working with, okay? So if you saw me deleting things, don't go back. You're working with something else and you just delete stuff. All right? Salva? Okay. Stanislas, translate please.
Okay. Après avoir effectué votre alignement, vous pouvez vous retrouver dans la situation où vous avez par exemple un des échantillons qui, après alignement, qui porte. Vous voyez ici, il y a des gaps, n'est-ce pas? S'il y a un grand nombre de gaps, vous pouvez ne pas avoir. Cet échantillon peut ne pas avoir un intérêt dans l'alignement que vous avez fait. Vous pouvez décider aussi de le garder. Mais si vous décidez de l'enlever, alors vous devez sortir cet échantillon-là et le faire regarder.
Okay, good. There are also instances when you might want to remove that. Because, for example, in this case, we only have one sequence that has, you know, the position starting from there up to position 50, 55, right? But maybe it is the reference sequence. And you want to always know which is position 1 and which is position, you know. If you trim it, you're going to start from a different position. So you may want to leave it because, you know, it's a short distance. It's not going to affect it. But you see, it's a different thing if, you know, maybe you're working with a gene or, you know, there are different dynamics. So again, context is important. All right. Phylogenetic tree now. You remember this? You remember this? We start with the first Q. Now we are here. We want to use IQ tree 2 and the alignments to generate a tree. Okay? So just like this is too many things. So just like MAFT, there is also an IQ tree server which you can use. Okay? You can upload your alignments and it can generate a tree for you. Okay? I'm going to send the link shortly. But the same thing I said about the MAFT server. You know what a server is? A server is like a computer somewhere that somebody allows you to use for free, right? But you see, because it is free, you can control how you access it. Maybe it has 200 GB. But then when you set something, you say, I will only give you 1 GB. Or 2 CPUs. So using a server does not necessarily mean that your stuff will always run faster. Okay? So just be aware of that. But sometimes for small data sets, it's actually useful to just quickly get a tree. Okay? Now the other option that you're going to use is command line. So we've installed IQ tree. So the same thing we did, I'm going to. So if you check through your installation, if you just do IQ tree, can you tell me if you see 2 versions of IQ tree? IQ tree and then IQ tree 2. Then, like you type IQ tree, then you tab and see what happens.
Okay. Est-ce que vous avez installé IQ tree? IQ tree, il n'y a pas de MAF. C'est déjà installé. Vous tapez IQ3 et puis vous faites tabulation. IQ3 puis tabulation. C'est possible. IQ3 et tabulation. Tabulation
IQ3, and then they developed IQ3.2, which should be much faster and more accurate. But I don't know whether nowadays, both of them do the same thing. But I prefer to run IQ3.2. Okay. Okay. So this is now just clean. So if I do IQ3.2 help, you can see that it has very many options. Okay? Very many. So this is always difficult to teach. Yesterday we did talk about models that are used in tree inference, okay? And we also talked about bootstraps, okay? So for the substitution models, there are many of them. There are very many. There are over 200. And either you can decide that I want to use a specific model, or you can have IQ3 decide which is the best model, and then it uses that model. Okay? So we are going to go with the option where IQ3 finds the best model, and then uses that model to run or infer the tree and get the tree.
Lorsqu'on veut inférer un arbre, normalement il y a plusieurs approches. On vous a montré qu'il y avait plusieurs algorithmes qu'on doit mettre en place. Et lorsqu'on utilise IQ3 possède toutes ces options-là. On peut faire comme on l'a fait pour MAF. On peut demander à IQ3 de trouver le meilleur algorithme, la meilleure approche pour cette possibilité.
Okay. So, why did I run my IQ3? There. Yes, I'm trying to see. Yes. Okay. I know I did run 3 different things. So, can you see my screen? So for IQ3, you need to give it an input -s. So this is your alignment file. So in this case, my alignment file is this one. Okay? Now there is the option for T. This is for threads. Your computer has a given number of CPUs, right? A lot of bioinformatics analysis are very computer intensive. It can decide to use all the CPUs on your system. So you can sometimes instruct it to use a given number of CPUs, or like just use whatever you find. Okay? So in this case, we are going to use auto, which means it will just determine which is the best number of CPUs to use.
Donc on va prendre l'option auto pour qu'il décide lui-même d'utiliser le nombre de CPU qu'il veut prendre. Donc si vous avez plusieurs CPU, on va choisir le nombre de CPU adapté pour réaliser l'analyse.
Okay. Now, when it comes to the models, you can either use a specific model, and the option for models is -m.
Donc si vous voulez utiliser un modèle particulier, vous utilisez l'option M et puis vous précisez le type de modèle.
I'll just shift back to the slides yesterday, where we were talking about,
parsimony.
You want parsimony?
Yes, maximum like.
Simple is easier. Remember, we're talking about different models, and here we're talking about transition, transversions, frequencies and things like that. You remember here? So there are so many models that you can have. Okay? One option is you can specify that I want to use this model. Okay? The other option is you can have IQ tree, find the best model and use that. Or sometimes you want to generate your tree using a different tool, not IQ tree. You can use IQ tree to just determine the best model, but not generate it. So anyway, we are using IQ tree, so I'll go back to my terminal here. So in this case, I ran my tree with a very specific model. So in my model, I've given it GTR plus I plus G. Now, what I'm saying here is that I'm letting all the parameters to be free. I'm saying that I expect some proportion of my genome to be invariant, which means they are going to be constant. And the proportion of my alignment that is variable, I expect that to change using a gamma parameter. Okay? So that is how I've specified my model. Okay? The other option is you don't know the parameter, you don't know the model, and you do not want to assume. So we say test. Test, find the best one, use it. Okay? Is that good? Now, in addition to the model, yesterday we talked about bootstrap, which is to know how reliable your tree inference is. So in this option, I'm adding an option minus B, which says, I want you to do 1,000 bootstraps. You remember, I'll just shift back here. So we're talking about bootstrapping. Where we're saying that you do bootstraps, you take a given number of sites and you do it again, and each time you generate a tree. So on the command line, we're saying we want you to do this thing 1,000 times. Okay? So the option that I want you to run is this one here. So you're going to say IQ tree minus S. Here, give the name of your alignment file. Okay? And then the rest of this will be the same as mine. Okay? So I'm just going to copy this, put it into that document. Or have you put it already, please? Okay, cool. Thank you. Now, off you go to the terminal. Execute this one.
James.
On veut exécuter IQ3. IQ3 va nous permettre d'inférer notre arbre phylogénique. Donc, en fait, IQ3 moins S, on lui donne notre fichier d'alignement. Après, moins T auto, qu'il ajuste lui-même ses paramètres. Moins M test, il va tester plusieurs algorithmes et plusieurs options. Celui qui est le mieux, il va faire son choix. Et le moins B, vous vous rappelez, hier on a parlé de bootstrap. Donc, il va bootstrapper, c'est-à-dire il va exécuter 1000 fois.
D'accord?
James, can you maybe add like just a couple of words to describe what those two different commands are doing? Just like a one-liner.
Okay.
For those who might have missed this session.
Si vous voulez voir les options, faites IQ-L. Et puis vous regardez chaque option, vous allez voir ce que la option fait. Quand tu changes, s'il vous plaît, votre fichier d'alignement ne porte pas le même nom. Vous devez prendre le nom de votre fichier d'alignement.
Just want to go through what IQ3 was doing, okay? For instance, did it finish? Okay, I think let's move. So you'll see that IQ3 did read in the file. The reason I like looking at this information because it tells you a bit more about your alignment, okay? So if you see up here, it's telling you the file that it read in, just to be sure that what you intended is what was read. And then it's saying, warning, 12,000 sites contain only gaps or ambiguous characters. So it's saying, from the alignment, there are 12,000 sites that contain either only gaps or ambiguous characters. Remember that there were large stretches of positions in our alignment that had lots of ends. Okay?
Yes.
So that's what it's saying. Now, secondly, saying that the alignment has 22 sequences. And that's what we expect, right? Because we know we have 22 sequences, correct? And then it's saying it has 197,206 columns. Okay? We know that is true because if we go back to early view, this is our alignment. At the bottom, there, we see 197,206, right? If I go back here, it's 197,206. So that's the number of positions, okay? And then it's saying we have 721 distinct patterns, okay? Remember, when we are building a tree, we are using mutations, right? These mutations are patterns that direct how the tree is made, okay? So remember what it's saying is that out of the 197,206 positions, there are only like 721 positions that are being used to infer the tree. Again, remember this is a DNA virus. So it's different from an RNA virus. So there's very few mutations that are actually used to make the tree, okay? And then there are 6 parsimony informative, like simplest solutions. You remember that? 20 singleton sites, so positions where, you know, there's a difference in only a single sequence. And then there are 170,000 sites that are constant, which means they are the same across all the 22 samples. Okay? That probably tells you that you could reduce the size of that alignment and probably it will change very little. But you'd have to know where these 721 sites are. Because I would also guess they're distributed across the genome. Okay? Anyway. So then it read in the sequences. Then it also does its own, like, sort of QC. Okay? And you can see that, you remember we had 3 sequences that had a very high number of N's. From epi to me, you remember epi to me, we had this file, right? And one of the sequences had 96% N, another file had 38% N, another one had 87% N. Let's see if we can find them here. Of course, we can see there is this one that has 96% N, this one has 87% N, and IQ3 thinks has failed. Okay? I don't know what it bases on entirely, but again, you know, this can also help you decide whether you want to remove those sequences or not. Okay? Now, we did say that, you know, remember the option -T? We said auto. Your computer has a given number of CPUs, right? So here it has determined that the best number of threads to use is 4. Okay, so it's using that. The other thing that we said was that test different models and pick the best. So here you can see that, you know, it's testing model number 1, giving the likelihood, right? And also like doing this Akaike information criteria with the correction and also the Bayesian information criteria. So it's giving these metrics, assessing each model and giving an assessment score. Okay? Stanislas is a statistician. We know much better about these things than I do. So you can see that, you know, it's testing about 87 models. Okay? Then at the bottom here, based on the AIC, the best model is Kimura 3 parameter plus F plus I.
Est-ce que vous avez compris ce qu'il a dit? Rappelez-vous que quand on était en train de faire notre modèle, on lui a dit on a mis auto, n'est-ce pas? Auto, ça veut dire qu'on lui demande de choisir le meilleur modèle pour nous. Donc, voici la liste de modèles. Il y a plusieurs modèles. On va avoir, à mon avis, 71 modèles. Et il va tester ces 71 modèles pour évaluer quel est le meilleur modèle. Lorsqu'on veut évaluer des modèles, on utilise ce qu'on a. On utilise des métriques qui nous permettent de voir quel est le meilleur modèle. Donc, ça, c'est le maximum likelihood. Ça, c'est le AIC, c'est le critère d'information d'Akaik, qui est une métrique qu'on utilise pour évaluer des modèles. Le critère d'information d'Akaik, dans sa version corrigée. Et puis le BIC, c'est Bayesian Information Criterion. Et donc, il va computer tous ces modèles-là en regardant ces métriques-là. Donc, n'oublions pas qu'il a computé combien de modèles? 87 modèles en regardant combien de critères? 4 critères. Donc, il dit quoi? Selon le critère 1, le meilleur modèle, c'est le critère basé sur Kimura. Selon le critère d'Akaik, voici le modèle de 1. Selon le critère bayésien, voici le critère 1. Et puis le meilleur modèle, quand tu regardes tout ça, il dit que c'est celui-là selon le BIC. Donc ça veut dire qu'il va computer plusieurs modèles, 87 modèles, sur plusieurs métriques. Et il va voir quel est le meilleur modèle. Oui.
C'est normal qu'on ait des modèles qui sont différents.
Ouais.
Yes is what?
Yes. Degrees of freedom. So, if you remember your statistics, so I'll have to ask the statistician. I know between AIC and BIC, usually BIC is more preferred. Okay? So often you would want the metrics from AIC and BIC to agree, But where there is disagreement, they will always prefer the BIC, whatever model is selected by BIC. Okay? Good? So now, after getting the best model, then the tree is run using the model that was selected, which is HKY. Hashigawa, Kimura, and Yano or something. I don't remember who those three people are. But, you know, when you're writing your paper, you need to report the model that you use to generate your tree. Science class, tell them that.
Lorsque vous êtes en train d'écrire votre papier, vous êtes obligé de dire quelque chose sur les critères et le modèle que vous avez pris.
So you can say, I used the model test in IQ3, and the best model, c'était H code Y.
Il ne faut pas venir dire j'ai utilisé juste IQ3.
What?
This model.
Yes.
Based on it. And the best model is.
Yes. Good. So then, you know, we generated the tree, and you can see that, you know, you can see that the tree search went through different bootstraps, and when it got to like around 600, there was no further improvement. Okay? And then it stopped.
Quand on a le fichier, on va utiliser.
Now, we want to understand the tree. There are different tree formats. Okay? Phylogenetic tree data formats, layouts, visualization tools, and also how to visualize a tree with metadata. Okay? So tree data format, so this is typically a text file. Okay? But it is a text file, and there are different formats. So the first one is NEWIC, which will have some information on the tree topology. We have Nexus, which will have tree topology and metadata. Okay? Then we have Phylo-XML, tree topology, metadata, and more information about the tree nodes. Then we have JSON file, which, similar to Phylo-XML, will have tree topology, metadata, and some information as well. Okay? So you can see this is the simplest. Okay? And we'll just have a look at what it looks like. So the NEWIC format, as we've said, has a tree topology, and this is represented as parentheses. So here, this is the tree. This one, this simple line. How many tips do we have on that tree? No. Yes. Okay. No.
Ok. Lorsque vous inférez un arbre sur l'arbre produit se présente sous plusieurs formats. Il y a le format NEWIC qui représente uniquement la topologie, le format Nexus qui représente la topologie de l'arbre plus les metadata, le Phylo-XML, la topologie, les metadata et bien d'autres informations concernant les nœuds. Il y a le format JSON. Donc, si vous regardez le format le plus simple, c'est le format NEWIC. Comment est-ce qu'il se présente?
So NEWIC format is the simplest.
Le format le plus simple, c'est le format NEWIC. Et c'est comme ça qu'il se présente.
And if you open a NEWIC file, it will just have information like this. Okay? Now, assume that you have a tree file that has this information. How many tips do you think are in that tree?
Si vous avez inféré un app et on vous a donné le format New Week, supposons que ce soit celui-là. Combien d'échantillons vous avez à l'intérieur? Combien de feuilles vous avez à l'intérieur?
1, 2, 3, 4, 5. Okay? So normally you'll have more information than this because we also have branch lengths. Okay? But this is just to show generally how it looks like. Okay? All right. And in fact, we can be able to see this. Let me just show you. Okay. So we don't even need to zoom with this. I thought I could zoom into this thing. Yeah, so zoom in. So now there's no shortcut for it. This is annoying. So I have to do this every day. Now, can you see this?
No.
You don't see.
Maybe just copy paste it into Word.
Or you can copy and paste it into the document we've been using the entire day.
Please. Copy it. Okay, I'm coming back to you. Voilà. All right. Can you see now? Oui. So you can see we have the names of the different tips, and we also have a number after a colon, right? And this refers to the genetic distances that we talked about. So this is how a NEWIC file looks like. Okay? Now, I'll go back to my slides here. The next format we are going to talk about is a Nexus format. So the Nexus format has the tree topology. So the tree topology is how the tree looks. Okay? So it has the tree topology and associated metadata. So for example here, it starts with the word #nexus to show that it's a Nexus file. And then we have, you'll see that we have two sections. So it says begin taxa. So this is a section where it talks about the taxa or the tips. So it's saying that we have number of taxa equal 5. Okay? And it's listing them taxa A, B, C, D, E. Oui? Then end. Fini. Okay? And then we go to the second section, which says begin trees. Okay? Then it says tree, and then gives the name of the tree. And then you'll see after the equal sign, it gives the NEWIC. Okay? And then we have end. So I know the tree we generated is NEWIC, right? Let's try and make it Nexus format. So don't worry about what I'm doing. Don't struggle to do what I'm doing, because you don't have figtree at the moment. So I'm going to open this tree on figtree. So figtree is one of the trees, of the tools that you use for visualization. But we'll talk about that shortly. So that should be this tree file. And then we have our tree. Just okay. So we have our tree, right? If I want, I could even like go to the branch levels here and display the branchlets, which are pretty small. Okay, but it's
Font size.
okay. You can see that. Okay, but I'll remove them because they are not necessary. All right. So right now, our tree does not have any metadata information. Okay? But let's create some fake data. So I'm going to here create a new annotation. I'm going to call it country. Okay? And I'm going to say that it's a string. There are different data formats. You know, like there's an integer, which is a number. There's real number, which should be able to accept like decimal places. There's a string. There's a boolean. Boolean is true or false. And then you have a range, which is like giving a range of numbers. So mine, I'm going to say it's going to be a string. And then I say okay. And then I say done. Then, because I want to move fast, I'm going to select this node here. And for this taxa, I'm going to annotate. And I'll say country USA. Okay? And then I'll click this one, this one, this one. I'm going to annotate. Let's say country. Who wants me to use their country? Burundi. And then I'll select these two here. And I'll annotate them. DRC. Okay. Now, you remember I opened this file and it was only Newick. But I've given them a new annotation, metadata, and saving. Now, this is the same file. Can you see what has happened? Now it's a Nexus file. At the beginning it says Nexus, begin taxa, dimension, we have 22 sequences, and it's giving tax labels. So the list of sequences here, and then we have metadata, country, US, country, Burundi, country, and then we have a section here that calls the tree. Okay? Then for this one, at the bottom here, because we are using figtree and it has its settings, so it has also added a section at the bottom. So, like, don't always expect this will happen. This is specific to figtree. Is that okay? Do you see the difference now? But you can see that this section for the tree should be the same as the old one. Okay? So I can save, well, I shouldn't have done this, but I can export this as, of course, we've already saved it as Newick, right? So I can save all trees, okay. I can use the same name. When it's Nexus, I'm putting the extension .nex. Okay? I'll save that one. And then I'm going to export this same tree as Newick. Okay? NWK. So I have two trees here. This is the nexus. This is the network. When you see the network, just the tree. But the nexus has a lot more information. So this didn't work very well. But I think if you automatically save it, you should have much more information like this. Okay? Good. Now we are moving on to the next format, which is Phylo-XML. So again, this has two topology metadata and some detailed information. This is typically used if you want to render. It's very good for like rendering trees on the web. Okay. So I have never used Phylo-XML myself, but I just thought it's good to show you what it looks like. And this is the format. So you'll have always like categories. So it's telling you phylogeny rooted, whether it's true or not. And then you have different clades, and the names, and different sections. Okay?
Le format Phylo-ML, si vous voulez, par exemple, visualiser votre app sur Internet et autres, c'est un format qui est adapté.
Il y a le site Phylogenetic. Quand tu travailles sur cet outil-là directement, tu construis sur la base des aliments, tu veux générer ton app automatiquement sur Internet, donc avec le site Phylogenetic ML, donc le format par défaut qui te donne, en fait, c'est ce format. Il y a un site.
Okay. Good. Okay, the last format is the JSON format. So slightly different, but quite similar in structure with Phylo-XML. And it will look like this. It will tell you about like the name, the roots, the children, and such kinds of details. So I think figtree should be able to give us this same tree. Let's try and export it as JSON. Okay, I'm going to include annotations here. So the extension is going to be JSON. So I'll just try open that. And you can see how the structure is. Okay? So you see that, you know, it's quite different from the Nexus and also the network. Okay?
Ce format-là, c'est le format qu'ils ont.
So the question at this point is, which format should you use? Okay?
Quel format vous allez utiliser?
Which format should you use?
Celui qui a recommandé. Qui est recommandé? Depuis ce qui est recommandé.
And your answer is this slide. So, different tree visualization tools that you're going to look at are always very specific about the input they want. If a tool says that I only use JSON, it will not accept Nexus. Okay? So you need to think about the tool that you're going to use. Okay? So as you think about the tree visualization that you're going to use, it is recommended that you actually export your tree file in multiple formats. That ensures that if you have different tools that you want to try, and you're going to talk about why you want to try a different couple of tools, you're ready, like you have the files ready for you to use for the different tools. Okay? Now, we have also different tree layouts. Yes. So there are different tree layouts. So here I've just included, there's rectangular, rounded, rectangular, ellipse, slanted, circular, fan, unrooted, timescale, network, etc. There are so many.
Il y a plusieurs manières de présenter un arbre. On peut présenter l'arbre au format rectangulaire, au format circulaire et autres.
C'est le mode circulaire.
Et il y a Il y a plusieurs façons de faire.
C'est ça.
So each format usually has advantages and disadvantages. Also, like how you want to communicate. Okay? Now, if you look at this is the same tree, but in different formats. So we have your phylogram here. This means that they respect the genetic distance. So you have rectangular, rounded rectangular, slanted, ellipse, etc. Here you have unrooted trees. You remember yesterday we talked about unrooted, so it doesn't have a root. So here you also have, equal angle, daylight, I don't know, all these kinds of different, different tree formats. And then at the end, we have the cladograms. So cladograms, here the branch length does not matter. You'll see that all the tips are exactly at the same point, whether it's rectangular or circular. Okay? So again, people use cladograms for different reasons. Okay? But all you need to know is that there are different tree display formats. Okay? And I can just quickly take a look back at my tree here on figtree. So if I go here at the top, currently we are on rectangular. Okay? I can make it to be circular. I can make it to be, look like the star-shaped or unrooted. So let me just remove the tips. Okay? So that is the same tree. That is the circular mode. And that is the rectangular. Okay?
Ça veut dire que dans le format cladogramme, là, les branches en même temps.
Si un cladographe ne fait pas comme l'assistant génétique, comme
So, and I think this should also do the, no, that is just only, I don't know, I thought this also does the cladogram thing.
should do.
We had a cladogram option. Not seeing it now. Okay. We can also do cladogram here. See? So that option is available. So, I'll go back to my slides. So, the rectangular one is the one most people use. We always use rectangular. And because it's good at representing the hierarchical structure, which again, remember, phylogenetic tree is about, the ancestral relationship. So rectangular is always really good because the information is clear and straightforward. The unrooted, we said you don't put a root because you want to focus on relationship between taxa without looking at the direction of the evolution. Remember that? So with the rectangular, often you can see that direction. With unrooted, you just want to look at the relationship, but you don't care about the direction of the evolution. Okay? And then we have circular. Circular, mostly we often use when you have very large trees. Yeah? I think you've seen people who have like thousands and thousands of tips. It becomes very difficult to put thousands of tips on a rectangular tree. So often we do a circular.
Si vous avez un très grand nombre d'échantillons sur votre table, le format rectangulaire est un peu plus petit. Donc le format circulaire dans ces conditions est très avantageux.
La forme s'affiche mal.
Si tu as un grand nombre de formats rectangulaires, si tu veux faire des tests,
J'ai un exemple, en fait, où
No, you didn't give any specific instructions. It's tea time now, so if you want to come
très bien en format rectangulaire de circulation. C'est vraiment
it's
emmêlé,
tea
j'ai
time
du mal
now, so if you want to come to tea, then we'll be through this.
Non, c'est pas mal.
Yes, yes, yeah, yeah. You can come straight to it.
Comment ça tu vas faire dans son plot?
Okay, let's go. So then there is the force directed network trees. How many have used microbe trace before? Microbe trace. So networks, like, have you seen how they represent like social contact patterns? This person contacted this person. Okay, I can show you an example later. So it's a different kind of tree. There are people who think it's not a proper phylogenetic tree, but you know, we can talk about that. And then we have a time tree. So a time tree, the branch does not just represent the genetic distance, but is also representing time. So the branch length is calibrated by time. Okay? Any questions? Yes. So that's a good question. The first thing, the way I would answer this is, first, you need to know the behavior of the tool that you're using to generate the tree. There are some tools that automatically, like roots, do midpoint routing. I'm not sure whether IQ3 does that by default, but probably not. It could just be, let me actually test this out. No, it doesn't by default. So I would say, in general, it depends on the tool. Some will route it based on like just the looking at this, the nature of the sequences, right? Some will route it if you explicitly say that I want to route it based on this. Some will do midpoint routing automatically. I don't know if, you know, like, if you're not working with that pathogen and somebody gave you a tree, it would be obvious that the tree is rooted. I don't think there's a way you could obviously say that unless you know, for example, like, oh, I know that's the oldest sequence and it's actually, the tree has been rooted using that particular sequence. For midpoint routing, it's usually more easier to spot because usually it's like trying to place the root somewhere in between the two most divergent sequences. So often the root and probably the youngest tip, right? So if we look at this unrooted tree, because I don't think IQ3 doesn't root the trees, and for example, control and repeated with IQ3, okay. Yes. Okay. Yeah. So here I've done midpoint routing. Okay. So midpoint routing, people often use it just to give the tree a bit of a balance. Because if you look at this tree in this manner, you know, there are tips. Let me just get the tip levels. There are tip levels here. You can't see a bit of a structure, right? But when I do the midpoint routing, so it's essentially putting the root somewhere in between the two most similar sequences here. And you can see that now there's a bit of structure. You could say, well, there appears to be like two big clusters. You know, there's this one that comprises of two sequences and this upper one here, right? And even for this one, you can almost see like there's some directionality. So that's why people often use midpoint routing. Again, before you decide how you want to route your tree, again, this is why I say domain expertise is quite important. Because you also don't want to end up with the wrong interpretation of the tree. I mean, in the unrooted tree, clearly, I can also see that, you know, these two sequences are quite different from this other cluster of sequences, right? So, can you see that? Like these two sets of sequences here. They cluster quite differently from the rest of this, right? Such that when I look at the midpoint rooted tree, it's not giving me anything different from that one. It's just that now it's better to visualize.
Qui peut me dire ça en français? Désolé, j'ai pas suivi.
En fait, lui, il est en train de Stephen qui a posé la question sur le fait d'appliquer le libre point. En fait, ça consiste en fait juste à donner la structuration à l'arbre. Tu peux avoir un arbre génétique. Tu vois bien qu'il y a une distance en fait comme il a affiché son premier James. Voilà, donc bon, je parle de ça. En fait, là, tu vois que les séquences, en fait, ils sont différents.
The best format depends on your tree. Good answer, right?
Les branches qui sont entre, par exemple, les deux séquences qui sont en haut et celles qui sont en bas, c'est tellement proche que tu as du mal à voir si vraiment elles sont éloignées ou pas. Donc le 8 points qui te permet juste le fait d'élargir la séquence, me zoomer au fait sur ta séquence, pour mon sur ton arbre génétique pour avoir une meilleure structuration. Afin de voir bien interpréter.
Well done.
Elle a bien traduit. Ce qu'elle a dit, c'est juste.